Hey everyone, I want to talk to you about something that is not directly part of your homework, and it's not a thing that we're going to have problems on, but it is a thing I want to explain because it will maybe make some of the stuff that we're going to do a little bit clearer. And if you read your book, it'll make what your book does a little bit clearer as well. So let me just kick it off with the whiteboard here. So it's about transforming distributions. So if I have a set of numbers and I take away the same number from everything in that set, the mean of that set has the same number taken away from it, which I hope makes sense. I'll demonstrate in just a second using sheets. But a similar thing happens with the standard deviation, where if we divide everything by the standard deviation, then if we divide everything by a number, the standard deviation gets divided by that number. So a common thing to do in both cases is to subtract the mean from everything to make the mean 0. And similarly, we can divide everything by the standard deviation and make the standard deviation 1. So I want to show you that because that seems like a thing that might require a little bit of convincing. So I'm just going to do this. Let's see, norm. And let's do like 10 and 5 here. All right, so I'm going to make what, like 10 numbers here. That would be convincing enough, I hope. So there's some random numbers there. I'm going to find the mean. Average of A1 through A10. There we go. Yeah, so here's my mean. I don't know, it's about what you'd expect, right? A random data with a mean of 10 is going to have a mean that's close to 10, but not 10. And then I'll do the standard deviation too. A1 through A10. All right, so there's the standard deviation. Okay, so now what I'm going to do is I'm going to make another column where I divide or not divide everything. I'm going to subtract first. I'm going to subtract the mean from everything. So if I do equals A1, I better make this here. There's a trick. I don't know if you guys know this trick in sheets. So I'm going to use two tricks here. Trick number one is I'm going to do that, right? So I'm going to say that B1 is A1, and then I'm going to do stuff to it. So I'm just going to incorporate A1 into the formula in B1, which is totally a thing you can do. You can also, if you just want to copy, I can just say it's A1. The other thing I'm going to do is I'm going to, do I want to use these yet? Yeah. So, no, not yet. No, this is okay. So A1 minus the mean, or it's called means, average of A1 through A10. Right. So this number right here is just this one if I took that away. All right, so that's why I get a negative number. So I'm going to do the same thing. So here's where I'm going to use the trick. Now, let me show you something. So if I fill this down, it'll fill in all the numbers, but then it'll take the average of the wrong things, right? It takes all these numbers and it increases them since I went down here. I still want it to be A1 through A10, not A10 through A19. So what I'm going to do instead is, no, I don't want to do that. I want to just grab these and delete them, is I'm going to use this. It's not a trick. It's just notation that you can use in spreadsheets. So I don't want that number to change. I want it to be A1 through A10 the whole time. And if I put a $sign in front of it, it won't. That says fix the thing that comes after this. So now, like this is the same, but when I expand this down, even down here, it's still A1 through A10, right? The $signs just mean don't let this thing change. And now, if I find the average, it should be 0, B1 through B10. And indeed, it is 0, right? And no matter how these things change, no matter how often they change, this is always going to be 0 because I'm taking away the mean. And if I find the standard deviation here, it should be exactly the same because I haven't divided by anything. B1 through B10. And indeed, look, those guys are the same number. Now, if I do the same trick again, and I divide by the standard deviation, so I'm going to do equals B1 divided by standard deviation of B1, but I don't want these to change, B1 through B10, 110. And then, of course, I'll fill this down. Okay, well, great. What's that mean? Well, now because I divided by something, that actually won't change the mean. So all dividing by something does, if your mean is 0, all dividing by something does is squish it together. I can maybe show you that on Desmos in a little bit, but for right now, what I'm going to do is just believe me, that's what it does. It squishes everything towards the y-axis. So if your mean is on the y-axis, it just pulls everything in, but doesn't change where the middle is, which is what the mean is essentially finding. Median's the middle. The mean is technically where it balances, but it doesn't change that either. It's still at 0. So if I've done this correctly, C1 through C10, mean is still 0, and the standard deviation should be 1. C1 through C10, and lo and behold, it is. So you can see that I've just done this with a bunch of random data, but if we do it to whole distribution, which is just an infinite number of points, then the same exact thing happens. We take the distribution, we shift it over to 0, and then we squish it so that its standard deviation is exactly 1. And you might say to yourself, fantastic, why would I care about this? Turns out, this is a thing that you've done before, believe it or not. I just didn't call it that. So let's look at, what do I want to do here? Whiteboard. Okay. So let's look at z-scores. So if you recall, we have the concept of z-scores. I'm sure you probably recall that. Let me draw here. Okay, all right, good. So I know that if I have a distribution called capital X that is approximately normal with a mean of mu and a standard, why am I drawing so tall? I don't know. I don't know. I'm just going to go with it. Standard deviation of sigma. Then we know that the z-scores of things in that distribution are this. Z is equal to X minus mu. So notice what we did there. We subtracted off the mean, and then we divided by the standard deviation. So what we're really doing is we're taking the distribution X, and when we find the z-scores, if we find the z-scores of everything, we're turning that into the distribution capital Z, which is N01, also called the standard normal distribution. So little x is one element in big X, and when we find its z-score, we turn little x into little z, and then big Z is N01. It's the standard normal distribution. This used to be a super common thing to do in statistics, and frankly, it still is, but it used to be more common because there were tables and other things published that told you important values in the Z distribution, but not for every X distribution, right? So if X is like mean of 10, standard deviation of 5, we don't know what the various critical values are, right? I know, like, we could know that we needed to go 1.96 standard deviations to the right, or to the right and left of the mean, to get 95% of or capture 95% of the data in the middle. But you could also, the way you knew that was from this distribution, because you needed to go 1.96 to the left and right to get 95% of this. So what people ended up doing was you would transform your data into this, right? You would do this exact thing right here to put it into this form. So you would have this set of data that's not actually a normal distribution. Maybe it was from a normal distribution, but you would calculate the z-score of every point in the data set, and that would make it so that your data, instead of fitting into this distribution, now fit into this one that you knew a bunch of things about. So this is where transforming data comes in handy. Now, you might say that doesn't look like the exact thing I remember from a z-score. I remember sigma over root n. Well, if you recall, the sampling distribution capital X bar, if X was this thing over here, n mu sigma, then capital X bar was approximately n mu sigma over root n. And so when you calculate the z-scores of this, now notice this is a normal distribution. This is what's called standardizing. I think I call it normalizing later. That's dumb. If I wanted to standardize this distribution, turn it into the standard normal distribution, well, I just do the same thing. I subtract off I subtract off the mean and divide by the standard deviation. Well, mean is mu and standard deviation is sigma over root n. And the things in capital X bar are not x's, they're sample means. So this is little x bar here, which is just one particular sample mean. And we subtract off mu and divide by sigma over root n, right? And then z is again in 0, 1. So what we're really doing is we're standardizing the distribution x bar to be the standard normal distribution that I have written in lowercase, which is bad. That's not correct. Should be uppercase. This is capital Z. There we go. And that's what z-scores are. Z-scores are, sure, it's the number of standard deviations away from the mean any given data point, or in this case, any given sample mean is. But another way to think of it is that you're transforming the distribution capital X bar into the distribution Z. And this, I don't think we've done too much with z-scores. I introduced them, but it's not like the biggest deal. However, oh, I'm sorry, I don't know what I've got coming next. Oh yeah, I used the wrong word here. I'm sorry, this should not be normalization. This is standardization is the word I wanted there, sorry. Standard, now it's check for some reason, there we go. Standardization with 2 samples. So what we learned about when we were combining normal distributions was that if we wanted to find, I don't want to say this, A minus B, right? So if we have a, that's not the right. If I want to do A minus B, that was, and again, so A and B are normal distributions here. I'm working with everything normal because that's what we knew how, that's what we learned how to combine. So this is n mu A minus mu B, the standard deviation of square root of sigma A squared plus sigma B squared. I always give myself too much room there. It's fine. So I can standardize that. I can standardize that to z, I don't know, I said this little z equals, well, everything in A minus B is, what do I want to say here, is an A, I'm going to call it XA and XB, right? So this is XA minus XB, because that's one element of A minus B. It's something in X, or something in A minus something in B, minus the mean. Well, the mean of our distribution is mu A minus mu B divided by the standard deviation. And so now, this distribution here that I'm highlighting in pink has turned into, I'm going to leave myself a little bit of room here, this one. So I'll give you a little heads up. Where we're going with this is t distributions. So t distributions, as you might remember, only approximate this distribution right here, n0, 1. They don't approximate any other ones. So what we have to do when we're calculating our t-scores for this 2-sample case is we have to turn this distribution, which I'm going to do in just a second here, into this one, and then approximate this with t distributions. So that's the idea. That's really what I wanted to show you here. So let me erase these things. I also want to make the point that, well, I guess I'm going to need an extra page here. Ooh, that's going to make my my things out of order. That's okay. I think we can fix this. Sorry, I got a couple pages set up here. So this works with sampling distributions as well, of course, right? Because they're normal. The sampling distributions I'm thinking of, though, are like x bar A minus x bar B, and these are supposed to be capitals, just writing them a little bit smaller. We know that this is n mu A minus mu B for the mean, and a standard deviation of this guy, sigma A squared over NA plus sigma B squared over NB. So as you can imagine, when we normalize this, we get Z equals this thing we've got. So we've got x bar A, that's lowercase x bar, minus lowercase x bar B. That's one element of this, that's a purple. That's one element of this distribution. And then we're going to subtract off the mean, which is mu A minus mu B. And we're going to divide that by the standard error, or standard deviation of the sampling distribution, which is this guy over here. So that is going to be something that I don't think I'm going to be able to fit here. I apologize. I'm just going to draw an arrow and say it goes right here. Right. And so then the distribution Z, capital Z, is again N01. Because all we're doing each time is taking one element in our distribution. We're going to do this for all of them, of course, but one element of the distribution, subtracting off the mean of the distribution, and then dividing by its standard deviation. And so that always gives us the same distribution back, or that always gives us N01, which is the standard normal distribution. That's why it's called the standard normal distribution. It's the one everybody turns everything into, essentially. So t-scores. Remember, t distributions mimic N01 specifically, right? So t with however many n-1 degrees of freedom approximates, I should have typed this, but whatever, N01. With the number of degrees of freedom, all that does is, so as n gets bigger, the t distribution just gets closer to N01, right? So if t is 1,000, it's, if the degrees of freedom is 1,000, then t n-1, t 999, is really, really close to N01. And technically, if you're into calculus, when n is infinity, t is equal to N01, right? It's if you take the limit as n goes to infinity, the thing you get is the normal distribution at the end. So that means that when we are doing our t distributions, what we're really finding, what we're really having the calculator do, right? We're not going to do this by hand, but we certainly could, is we are having the calculator turn everything into a t distribution. So what we say is that the t-score, instead of being the z-score, it's a t-score, is the same thing that we had before. It's x bar A minus x bar B divided by, or minus mu A minus mu B divided by the standard deviation. But since it's a t distribution, we're substituting s's for sigmas. So this is s squared, or sa squared over na plus, I'm going to put the square root on in a second, plus sb squared over nb. Oop, that's not the left side of a square root. Square root. There we go. It's that. So when you're finding that, so when we're turning everything into t distributions, this is really what we're doing. We're taking all of our variables, so all of the xa's and xb's, excuse me, x bar a's and x bar b's, and that are in our distribution, and we are subtracting off the mean from them and then dividing them by the standard deviation. And so this thing, instead of being a Z, it's a T. So we have the T distribution with, I'm just going to put DF here. Because the way you calculate the degrees of freedom when you do this transformation is not simple. It is, in fact, a giant mess if you want to do it correctly. Your book has the formula, and I meant to look at what page that's on. It's in chapter 9. No, it's in chapter 10. It's in chapter 10. If you want to go look it up, I should probably find it. In fact, let me go ahead and stop the recording. I'm going to go find that right now. It's silly that I haven't yet. All right, I went and found it. So look in your book, it's in chapter 10 in the first section. And so you can see this is exactly what I was talking about, right? So that's their test statistic. I want to talk about what test statistics are in just a second. Here is the degrees of freedom. Notice it's a mess. This is not exactly a weighted average. I mean, it's kind of a weighted average of the degrees of freedom from each of the two samples. Oh, wait a minute. Pointing at it on my screen. Here, it's this. So it's in chapter 10, first section. Here's the formula for you. So this is the thing that I was just showing you, the T-score formula for 2 degrees or for 2 samples. This is the formula to calculate the degrees of freedom, and it's a weighted average of the degrees of freedom of the two samples, kind of. So, it's not exactly that, but you can see so this right here is the variance of your the variance of the distribution of the T distribution, and then down here we are dividing by, well, the variance of each of the samples individually, but weighted by 1 over the degrees of each of the degrees of freedom. So it's a bit of a mess if you want to calculate this, and so we're not going to. We're just going to have the calculator do it. And if you remember from my last video on confidence intervals, on 2 sample confidence intervals, when we got like 64.1159 or something like that, this is what was being calculated. They were doing this thing. So the degrees of freedom are not trivial to calculate here. That's why I'm just calling it DF, because it's that messy formula. Where was I going with this? Well, let's see what the next thing is. Oh, yes. Test statistics. I want to talk about test statistics. So a test statistic is just a statistic you do a hypothesis test with. That's it. We've used them. We've used Z statistics a little bit. We've used our most common test statistics so far has probably been the population or the sample mean or the sample proportion, right? Those are the things that we're using to find our probabilities. However, T distributions use a test statistic. They use the T-score. The T-score is the test statistic. And notice that statistic is defined by what you're really doing is you're transforming each X into a T. And then you're finding the probability based on T. And that's all test statistics are. They're just something that you transform your data into so that you can figure out some probability that you want, right? For us, it's been the p-value so far. There are other things, but it'll continue to be the p-value in general for us. So some other test statistics that we're going to get to are, I guess I'll write a couple of them. So F is going to be sigma 1 squared over sigma 2 squared. That's one that we're going to end up using. We're going to have chi-squared is observed minus expected squared over expected. You'll see what these things are when we get there. We're going to have R and R squared. We'll have alpha and beta. I guess those aren't actually test statistics. Those are something a little different. R and R squared, these are for regression. I'm not going to write the formulas here. They're big and messy, and I don't want to deal with them right now. But there are other things, like the test statistics get more esoteric as you get further on into statistics, right? So we're going to, I'll just give you a little spoiler here. When we do F, what we're going to be doing is we're going to be comparing two standard deviations to each other. We're going to get the ratio of two standard deviations to see what, well, you'll see when we get there, but it's to test to see whether several means are equal to each other or not. And that's going to take some explaining, but that is what we're going to do with it. But that's the basic idea is we wanted, you want some way to figure out if several means are equal to each other and you want to test them all at once. And somebody clever, in this case, Ronald Fisher, which is why it's called F, comes up with this method. It's called analysis of variance or ANOVA, which we'll get to. Don't even worry about it right now. But I just wanted to show you that test statistics get kind of ever more esoteric the farther you go. And if you can figure out what the distribution of F's are, then you can use that to find probabilities. So that's what we've been doing, right? We've been finding test statistics, but with t-scores, because we know what t-distributions look like. We'll eventually find p-values and probabilities with F statistics, because we know what F distributions look like. And we'll do the same thing as a chi-square. We'll do the same thing with chi-square distributions, because we know what those look like. Same thing with R and R squared, although those are a little bit different. But that's what test statistics are. And so don't be too afraid when we get this new statistic. The thing you want to keep in mind when we're finding new test statistics is what we're measuring, right? So when I'm introducing a new test statistic to you, like a chi-squared, I'll explain what O minus E is and E and why we're squaring this and dividing by E. I'll explain all that stuff when we're introducing it. And so don't necessarily worry too much about the details inherent to the calculation, although we'll do that. Worry more about what we're supposed to be measuring and therefore what big numbers or small numbers mean, right? And that's sort of the same thing with T's. If T is big, either big negative or excuse me, big positive or big negative, that just means it's far away from the mean that we were expecting, right? The mean of the expected distribution. That's really what a big or small t means. Same thing for Z, right? If the Z-score of some observation is big, that means that it is far away from mu. That's all it means. That's really what it means. Now, the interpretation of what that tells you, right? If we have a mu in a hypothesis test and we get some big X value, which turns into a big Z value, well, that means that was far away from what we were expecting, right? It's far away from the null hypothesis, which makes us want to reject the null hypothesis. Same thing here, right? So, or not here, but with t statistics, if we get a big T, it's going to be far away from our expected mean, and therefore we're going to want to reject the null hypothesis. It's going to turn out to be the same for these. If we get an F that is far away from 1, which turns out to be the mean of this distribution, or if we get a chi-squared that's far away from n, which turns out to be the mean of that distribution, n being the sample size, then we're going to want to reject the null hypothesis. So test statistics, that's what they are. Basically, just some transformation we do on the numbers that we have to turn them into something useful that lets us figure out something about the data set. So when they're talking about test statistics, if we're doing a t-test, the test statistic is a t. If we're doing a z-test, the test statistic is a z, or sometimes we just use x bar instead of transforming it into a z. It's actually what we've been doing, which is fine. It's the same thing. We're just leaving it untransformed. When we're doing an F test, the test statistics will be, unsurprisingly, F, and they'll go on an F distribution. When we're doing a chi-square test, the test statistics will be chi-squares, and they'll go on a chi-square distribution. So when you hear something about test statistics, that's what it means. It's just the statistic that goes with that test that we're doing. And this is pretty much all of them. I don't think I'm going to hit you with too many more. I think to do 2 sample, then we're going to do chi-square ANOVA regression. Yeah, and this is all those in there. So this is all the test statistics we're going to have for the rest of the semester, and I'll explain them as we go. So don't sweat them yet. I just wanted to point out that there's more of them and they get a little esoteric. And I think that's really all I wanted to say. Let's make sure I don't have any other, no, I don't have any other, I just have a blank page for some reason. I don't have anything else I wanted to say, so I'm going to go ahead and stop the video there. Thanks for watching. I'll see you guys in the next one.